Hello from West Virginia. I am still lost. Okay, well anyways, it's time for Joke of the Day, and this one is highly appropriate. I think you're going to love this. Why does Waldo always wear stripes? You know, where's Waldo? Why does he always wear stripes? He's lost kind of like I am, isn't he? Anyways, why does Waldo always wear stripes? Because he doesn't want to be spotted. Okay, so we are going to spot ourselves onto solving rational equations. I'm really just stretching these, aren't I? It's okay. Anyways, solving rational equations. We're going to do this in two parts. We're going to take a look at the basic type of solving rational equations here in part one, and then we're going to stretch that in part two into solving rational equations where we have a variable in the denominator. The examples that we're going to look at in this video are not going to have any variables in the denominator, as you can see. So we have a rational equation because remember, rational does not mean rational, dude. What rational means is can be written as a fraction. So I have a fraction here and I have a fraction here. Now when you have rational equations, there are two ways to solve them. Method one says, okay, I've got fractions in there and I'm adding these fractions. So what I'm going to do is retain the idea that I have fractions in here, and I'm going to say, what does it take to add fractions? And you're right, it takes a common denominator. So in this first method, what our first step is going to be is that we are going to get that common denominator, get the common denominator, denominator, sometimes I can't spell, which we lovingly call the LCD. So as we look at this rational equation, we're going to say, okay, what would the common denominator be for a 6 and an 8? What is the smallest number that 6 and 8 will go into? Not that will go into them. I'm not looking for a 2 here. I want the smallest number that they will both go into. Yes, the smallest number that they'll both go into is going to be a 24. So what I'm going to do is I'm going to convert everything into 24ths. Even back here on the other side of the equal side, converting everything to 24ths. Now let's think about this. In order to convert this to 24ths, we would say, if it was a basic fraction, we would say, well, that means we're going to multiply that 6 by 4. And we said that what we do on a denominator, we have to do on a numerator because we don't want to change the value of the fraction. We only want to change what it looks like. So remember, that's why we multiply numerator and denominator by the very same number, because 4 over 4 is a 1. And when you multiply by 1, do you change value? No, not at all. So that's why you multiply on the numerator and denominator by the very same number. And when I do, I get a 4x on this numerator. But the whole idea is that the x over 6 and the 4x over 24 have the same value. They take up the same space. Because if you look at this and you would simplify this fraction, 4 goes into 4 once, 4 goes into 24 6 times, you wind up back there at that x over 24. So all we are doing is we're converting these fractions so that they will have common denominators. So we're going to do the same thing here, and we're going to say, well, we're going to multiply that 8 by 3 and this numerator by 3 as well, giving me a 3x. Now over here, a couple of ways of looking at it. We could say, well, a 1 is just simply a 24 over 24, or we could say that if we put this 1 over a 1, we would multiply the denominator by 24 and the numerator by 24. Regardless, 24 over 24 simplifies to a 1. So we get that common denominator, we adjust all the numerators, and now take a look at this. Think basic fractions. In other words, if there was no x here, and you had a 4 over 24 and a 3 over 24, and you were adding them, what would you do? Certainly, you would add those numerators and you would keep the denominator. So you are going to add or subtract the numerators, and then you're going to keep that denominator. Very important. Superhero fractions, you keep that denominator. So now I'm going to do that idea, but notice what happens with these numerators. If it was just a 4 plus a 3, we would say it was a 7. But it's a 4x plus a 3x. Well, you can do 4x plus 3x. You know 4x plus 3x is going to be a 7x. And we're going to keep that denominator of 24. So what we have at this point is equivalent fractions. And the way that we're going to look at this is we're going to say, okay, pan balance idea here, because we've talked about this many times. Your equation is a pan balance. This equal sign is that fulcrum in the middle. So in this pan is that 7x over 24. In this pan is the 24 over 24, and it's all balanced out. So if it is balanced and therefore has equal value and those denominators are the same, what has got to be true about those numerators in order for them to have the same value? If these denominators are the same and they're equal, what has got to be true about those numerators right there? Exactly. They have to be the same. The 7x here, can it be anything other than a 24? No, if it's anything other than a 24, it's not going to be balanced, and we need it to be balanced. If 7x is a 21, it's like this. If 7x is a 50, it's like this. So I need it to be balanced out, and that means that 7x, let me put it in purple so it's in the right color here, that 7x had better be a 24. So basically, at that point, you can just drop those denominators. Drop the denominators. And I've left off number 6 here, and you're going to solve the resulting equation, which frankly ought to be pretty easy to solve. Solve the resulting equation. And you know how to solve this resulting equation. You know that at this point you're going to take both sides and you're going to divide it by a 7, giving you x equals 24 over 7. So that's the steps for method 1 that says I'm going to retain the idea that I have fractions in here that I'm adding. I'm going to go back to the idea of what it takes to add basic fractions. You have to get a common denominator. You have to adjust those numerators. You have to add or subtract the numerators depending on what it tells you to do. And you're going to keep that denominator. But at this point, because you've got a balancing act going on, the two fractions are equivalent, you can just drop the denominator and work those numerators. When you set those numerators equal to each other, then you're going to solve the resulting equation. Now, let's take a look at method 2. For those of you who don't like fractions, and I know there's many of us who don't like fractions, we can get rid of the fractions in one step. Very easy to do. And a lot of us are huge fans of this second method because it allows us to get rid of those fractions quick and easy. But what this second method does is it still utilizes that LCD. So I'm still going to utilize this 24 that I've got right here, but I'm going to handle it in a different way. What I'm going to do instead is I'm going to multiply everything, and I'm putting this in all caps because it's critically important, everything. And what I mean by everything is every single term. Multiply every single term by that LCD. Watch what happens. So let's go back to our x over 6 plus our x over 8 equal to 1. And instead of retaining the fractions, I'm going to take everything in here and multiply it by that LCD of 24. What that means is I'm going to multiply the first term by 24. I'm going to multiply the second term by 24. And I'm even going to multiply the other side by 24. What happens here is, notice, I am multiplying fractions. Oh, there's that stupid gang symbol again. It's coming back. It's always there. Get used to it. You are in my math gang now. So we're going to multiply fractions, and we know that means cancel in those diagonals. Here's what happens. Notice that when I put that 24 over a 1 and I check that diagonal, 6 goes into 6 once, into 24 4 times. What am I left with? Just a 4x. Notice the same thing happens right here. When I put this 24 over 1 and I cancel in those diagonals, 8 goes into 8 once, into 24 3 times. What am I left with? Just a 3x. And notice back here, 24 times 1 is just a 24. I have an equation that is very easy to solve. So once I've multiplied everything by that beautiful LCD, it clears out all the fractions, And once again, I have an equation that's pretty easy to solve. So solve the resulting equation. And so if I take this resulting equation and I say 4x plus 3x, I will get a 7x. Notice that that is exactly what I had right there. And I'm going to go through and divide by a 7. So you have got two methods that you can work with when you have rational equations, in other words, equations that have fractions in them. One is to retain the fractions, the other is to get rid of the fractions. Now, let me caution you. Most people fall in love with this method when they see it. I'm an enormous fan of this method. But you have to be aware that this method does not always work. You have to be very careful. This works when we have rational equations. What does that mean? What's the difference between an equation and an expression? Yes, an equation has an equal sign, an expression does not have an equal sign. So if this equal sign is gone and this is all I have, x over 6 plus x over 8, and that's it, I cannot do second method here. Because what happens here is, when I do this, I change value. When I take just this side and multiply by 24, notice that 24 times this x over 6 results in a 4x. Now remember, over here we said 4x over 24 and x over 6 had the same value. They took up the same space because a 4x over 24 simplifies to an x over 6. But a 4x, and that's it, just a 4x, does it simplify to an x over 6? No, they do not have the same value. And so therefore, when this equal sign is gone, and I simply take this and multiply it by 24, I'm completely changing value. That's not okay at all. It's okay over here because what I'm doing is I'm not changing value. So it's okay here. This first method will work all the time, even when that equal sign is gone. And if I had to add these two fractions, no equal sign, just a rational expression, and I'm going to add up these two expressions or two fractions here, then this first method will work. Because in order to add fractions, I have to get a common denominator. And so what I've done here will work to be able to add up those two fractions, and the result will be a 7x over 24. And that will be my answer for adding those two fractions. So what I'm trying to get at for you is this first method works whether you have an equation or an expression. This first method always works. The second method only works when you have an equation. It does not work when you have an expression. It works when you have an equation because you're doing the pay and balance idea. And when you multiply everything, every single term by that LCD, essentially what's happening is you're multiplying this side of the equation by 24 and this side of the equation by 24. You're doing the pay and balance idea. You're multiplying both sides by 24 and you're keeping it balanced. That's why the second method works when you have an equation. So, if you are somebody who gets confused about, well, you're telling me I can do this right now, but I can't do it later, and that will confuse you, then for you, second method doesn't work at all. You will always do that first method because the first method will always work. But if you are somebody who can keep it straight when you're allowed to use the second method and when you're not allowed to use the second method, this is a great method. I'm a huge fan of it because it wipes those fractions out in one step. So you don't have to know both methods. You certainly are going to need to know this method whenever the equal sign is gone and you're doing rational expressions. You will certainly need to know this method. But for now, you can pick between the two. So let's do one more example, and I'll do both methods just to make sure we're good and solid with it. Okay, so let's take a look at another example here. Notice that we have yet again a couple of fractions that are being added together, and so we can use that method one that says when we are adding fractions, we need to get common denominators. So the common denominator for a 3 and a 4 is going to be a 12. The smallest number that they will go into is a 12. So I'm going to convert everything to 12ths, including over here. So now I'm going to take that 3 and multiply it by 4 to get a 12, which means I multiply my numerator by 4, giving me a 4x. Here I'm going to multiply this denominator by 3, which means multiply the numerator by 3, giving me a 9x. Now if I put that 2 over a 1, that means multiply its denominator by 12, multiply its numerator by 12, giving me a 24. So I have common denominators all the way across, and then I think, okay, when I'm adding fractions, once I get the common denominator, what comes next? Yes, add those numerators. So a 4x plus a 9x will give me a 13x. And then remember, what do? Yes, I keep that denominator. Remember, you worked awfully hard to get that common denominator. Let's not mess that up. Let's go ahead and keep it. But at this point is when I look at this and go, okay, these are equivalent fractions. That's what the equal sign means. They have the same value. So if they have the same value and their denominators are the same, what has absolutely got to be true about these two numerators right here? Certainly, they have to be the same. That 13x right there had better be a 24. If that 13x is anything other than a 24, it's not going to be balanced. It's going to be all kicked out of whack. So the 13x had better be a 24. We know where to go after this. Pretty easy equation to solve. We just got to go through and divide by 13 on both sides. And so that means that my x is going to be a 24 over 13. Ta-da! Not too bad. But if you don't like that, remember your second method gets rid of those fractions in one quick and easy step. So in this second method, we're going to take that x over 3 and that 3x over 4 and even the 2. And remember, what we're going to do to get rid of those fractions is we're going to utilize our LCD of 12, but what we're going to do is multiply every single term by that 12. Multiply the first term by 12, multiply the second term by 12, and even multiply the other side of the equation by 12. Now, 2 times 12 is 24, and remember the beauty is what happens right here when you multiply those fractions, and you got that gang symbol. Multiplying x for multiplication, multiplying fractions means cancel on those diagonals, cancel up and down, and then shoot straight across. So what I'm going to do then is I'm going to say, well, if I put the 12 over 1, 3 goes into 3 once, 3 goes into 12 4 times, leaving me with a 4x. And then on the second fraction, again, put that 12 over 1, 4 goes into 4 once, 4 goes into 12 3 times, leaving me with a 9x. And I have a pretty easy equation to solve. I know that 4x and 9x gives me a 13x, taking me right back where I was right there. And I'm going to go through and divide by 13 and get once again a 24 over 13. So you can see either method's going to work. You just got to know when you can use it and when you can't use it. This works whether you have an equal sign or not. This only works when you have an equal sign. Now, we can check this to make sure that it's right. And if we go to check, remember what that means is I'm going to take that 24 over 13 and I'm going to put it everywhere I see an x. So 24 over 13 is going to go right here. And it's going to be divided by 3. Now there's that complex fraction idea, and we know that dividing by 3 is the same thing as multiplying by its reciprocal 1/3. So I'm going to make this a little bit cleaner, and I'm going to multiply by 1/3. Then I'm going to add 3 times 24 over 13, 3 times 24 over 13, but that's going to be divided by 4. And again, dividing by 4 is the same thing as multiplying by its reciprocal 1/4, or we can also look at this as 3/4 times x, which is a little bit easier to understand. So I'm going to take this as 3/4 times that x of 24 over 13. I better get a 2 when I do all that. Now remember, multiplying fractions means cancel on those diagonals, cancel up and down, and then shoot straight across. So when I look at those diagonals, 3 goes into 3 once into 24 8 times, and that will leave me with an 8 over 13. And then here on the next one, when I multiply those, because remember, PEMDAS, mode of operation, says do this multiplication and this multiplication before we add. So we're going to multiply. And here, nothing cancels on this diagonal. There's not a number that will go into 3 and 13. But on this one, 4 goes into 4 once, 4 goes into 24 6 times. Check up and down to see if anything cancels. 3 over 1, 6 over 13. Nope, nothing cancels. So I'm going to shoot straight across. 3 times 6 is 18. And 1 times 13 is 13. And now when I take an 8/13 and add an 18/13, I'm going to keep that denominator of 13, add those numerators. 8 and 18 gives me a 26. And 26 divided by 13, yep, it's a 2, all right. I created truth. That means that this is exactly the right answer. So I hope that helps with solving your rational equations. And remember, rational means can be written as a fraction. So therefore, oh, my set's falling apart again. Therefore, in order to solve those rational equations, you've got these two methods, remembering that this method works all the time, even when there is not an equal sign, but this method will only work when there's an equal sign. Okay, let's take a look at a third example here of solving our rational equations. Remember, in method 1, we're going to retain the fractions. Now, notice I've got 4 terms here, so what I'm going to do is put this over a 1 and this over a 1 as well. And once again, in that method 1, we're going to retain the fractions, so I'm going to find common denominators because I'm subtracting and I'm adding these fractions. So I look at the 5, the 1, the 10, the 1. What is the smallest number that they will all go into? Not the smallest number that will go into them, but that they will go into. Yes, 10 is the smallest that they'll all go into. So in this first method, I'm going to convert everything to tenths. Notice this one's already there. And convert this into tenths. So I'm going to take this 5, multiply it by 2, and take that numerator, multiply it by 2 as well. Now, 2 times 9x will give me an 18x. And then on this one, I'm going to multiply by 2, multiply my numerator by 2, giving me a 6. This one again is already there, so I'm going to not by 2, oh my goodness, I'm so sorry, by 10. Excuse me, blanked out there for a second. So I get a 30 over 10, that's much better. So I'm going to multiply this by 10, and multiply this by 10 as well, giving me a 90. So I have my common denominators all the way across. So once I get the common denominator, remember, if I'm subtracting fractions, I'm going to subtract those numerators and keep the denominator. So I'm going to keep that denominator of 10 and keep the denominator of 10 here, but I'm going to combine up these numerators. Now this is an 18x minus 30. Can I really take an 18x and subtract 30 from it? No, I can't. But what I can do is I can go ahead and write it as one single numerator, which will be very helpful. Here as well, can I take a 3x and add a 90? No, I can't. But once again, I can put them together like this as one single numerator. And the reason I'm doing this is because at this point is where I'm looking at this going, okay, this, believe it or not, is a single fraction. It feels kind of weird. It's a very complex fraction. But this is one single fraction, one single fraction. Notice that this says the two fractions are equivalent. They are equal to each other. And notice, too, that the denominators are the same. So like we have said, every single time when those denominators are the same and the fractions are equal, what does that mean about these numerators? Yes, they have got to be equal. So that 18x minus 30 has got to be the same as the 3x plus 90. And yet again, I have an equation that's pretty easy to solve. You know what to do with this stuff. So what we're going to do at this point is we're going to subtract a 3x, or you could subtract the 18x. It really doesn't matter. We've talked about that before. 15x minus 30 equals 90. So now I'm going to slide the 30 to the other side, and I'm going to add 30 to both sides. And so that'll give me a 15x equal to 120. And now I'm going to go through and I'm going to divide by 15 on both sides. And 120 divided by 15 is 8. There it is. Now, method 2, remember, says, I don't like those fractions. I want to get rid of them. I want to get rid of them as quick as possible. So method 2 says, I'm going to take my original equation there, my 9x over 5 minus 3 equal to 3x over 10 plus 9. I'm going to take that original equation and I'm going to multiply every single term by that common denominator of 10. So what I'm going to do is I'm going to multiply the first term by 10. I'm going to multiply the second term by 10. And on the other side of the equal sign, I'm going to multiply its first term by 10 and its second term by 10. Now, like we've said many, many times before, when you are multiplying fractions, cancel on those diagonals. So here, 5 goes into 5 once, 5 goes into 10 two times, leaving me with an 18x And then here, 3 times 10 is 30, so 18x minus 30. And on this side, once again, checking these diagonals here, 10s will cancel out, and I'm left with a 3x. And then 9 times 10 is 90. Notice that this is exactly the same equation that we had right here, so we can go and solve it as we did before. So another illustration of either of the two methods will work perfectly fine. Now remember, you can check this. As always, we can check. So I'm going to take that 8, I'm going to put it right here where the x is, 9 times 8 over 5 minus 3. And I'm going to put the 8 right here, 3 times 8 over 10 plus 9. 9 times 8 is 72. And over here, 3 times 8 is 24. And now if I want, I can go through and I can make common denominators all the way across, or I can say, okay, this is going to be, 3 is going to be, if I make a common denominator, 5. So then I will have a 15 over 5. And 72 minus 15 will give me a 57 over 5. And on this side, get that common denominator of 10. And so 9 is going to be 90 over 10. And 24 over 10 plus 90 over 10 is going to be a 114 over 10. And notice that if I divide both of these by 2, I will get a 57 over 5 like I got right there. So this does create truth, meaning that that is the correct answer. So I hope this helps with the idea of simplifying or solving your rational equations. And remember that in order to do that, you've got two methods. First method here says let's retain those fractions. Let's get that common denominator. Let's adjust those numerators. Let's combine them by adding or subtracting those numerators and keeping the denominators. Then let's drop that denominator because the two fractions are going to be equivalent, giving us an equation that's pretty easy to solve. The second method says I don't like those fractions. I'm going to get rid of them in the first step. And I'm going to utilize that LCD, but I'm going to multiply every single term by that LCD to get rid of those fractions and getting me to that pretty easy equation to solve very quickly. And remember, this first method works whether you have an equal sign or not, but the second method does not work if you do not have an equal sign. So if you can keep it straight when you can use the second method and when you can't use the second method, it is a great method to use. But if you can't keep that straight, this one works all the time. Hope it helps. Have a great day.